Yeah, welcome to this module on quantum error correction. In this video, we will briefly discuss some advanced concepts in quantum error correction that you can also study by yourself later on. Briefly a summary of what we discussed in the previous video. We introduced the surface code, which is one of the most successful error correction codes currently, although there are also alternatives to look into. One thing we did not touch upon is how do we do gates on our logical qubits. And there's one thing that is actually very easy to do, which is single qubit Pauli gates. We know that's easy because we discussed the logical X and the logical Z operators, which are really just these like cuts through the surface code. So we can simply just go along one cut, apply single qubit Pauli operators, and that's our logical Pauli gate. Similarly, any type of what we call a Clifford gate is actually somewhat easy to do if it's a single qubit Clifford, which you can do using standard techniques. Clifford gate here means it's either a Hadamard gate, a phase gate, or a Pauli gates. 2-qubit gates starts to get slightly complicated. So what you need to do here is, if you have two surface codes and you want to do a 2-qubit gate between them, you actually need a third surface code. And then you need to merge sort of the edges of these surface codes in a very particular pattern. And this whole business is called lattice surgery. And that way we can do 2-qubit gates. That sounds a bit complicated, but that's actually still one of the easy part. The hard part comes when we want to do something that is non-Clifford. A specific example of what we call a non-Clifford gate is the gate that gives a pi/4 phase on the 1 state relative to the 0 state. Non-Clifford gates are essential to give a quantum speed up for any type of quantum algorithm. So we need to be able to do these types of gates. An example on literature on how to do it can be illustrated like this. So here you see a picture of a surface code, slightly different colors than I used. And the way they demonstrate here, the equivalent of a T-gate on a surface code, is that you need to perform a measurement on the red qubits in the Z basis. Then based on the result of those measurements, you perform a conditional operation on the blue qubit. Then you do a Z rotation on that qubit, and then you measure in the X basis in the rest of the qubit, so in the X basis. This is equivalent to doing a T-gate and an X basis measurement. This is a bit complicated, but it turns out that when you do this operation, it's actually not fault tolerant, meaning that if you do slight errors in this, it propagates through the circuit in a way that it can lead to even more errors. So to get rid of that, you need to do this, but actually at least 15 times. And then you do lattice surgery between all of these 15 times to eventually get a somewhat okay T-gate. So this is really the hard part of quantum error correction, is how do we construct T-gates efficiently. And as a fun fact, it's so hard that when researchers try to figure out how much do we really need to do to run a certain quantum algorithm, they at the end, for the most part, only count the number of T-gates that they will need to do. Moving on to a different topic. I want to introduce a concept here, which is a specific notation that we use to describe error correction codes on a very abstract level. So in this bracket, we write NKD, where N is the number of data qubits, K is the number of logical qubits, and D is the code distance. And all error correction code can really be described by these three numbers. For example, the surface code, we have N data qubits, we have 1 logical qubits, and D, which is the code distance, goes as square root of the number of logical qubits. To understand how compact or good the code is, sometimes we talk about the rate of encoding, or the encoding rate, which is K divided by N for a fixed amount of D. And in the surface code, that really scales as 1 over N, which in this case would scale as 1 over D squared, which means that if you go to larger and larger codes, the rate gets smaller and smaller, which means we have a vanishing rate. That means there's a big overhead or quadratic overhead if you want to go to more and more protection in terms of D. There exists a certain type of error correction code called the good low density parity check codes, or good LDPC codes for short, that has the property that in the limit of large number of qubits, the number of logical qubits and the code distance still scales approximately linearly with n, which is the number of qubits, meaning we have a constant rate, at least asymptotically. In such a code, we can potentially encode many, many more logical qubits in fewer physical qubits as compared to, for example, the surface code. But this is still a very hot topic in research, and the details such as how do we decode it, how do we really construct all the stabilizers in an efficient way, is still very much work in progress. So with that, I want to sum up finalize this series by talking about some of the challenges going forward. So one of the key things that was briefly mentioned, but I want to highlight it as the final challenge, is that all these error correction schemes really only work if the physical error is below the threshold error for your quantum error correction code. We only get there if we have good enough quantum hardware such that we start from a point of view. So a key challenge to build better quantum error correction codes is to build better quantum hardware. The second challenge is that we always need better error correction code. I mentioned the example of good LPDC codes, but other types of codes could also be useful in trying to bridge the gap between where our current quantum hardware is and what is really needed to run the best quantum algorithms. So with that, thank you for attending this module.